So predicting the type of radioactivity, and I think some of you had questions about this on Tuesday. How do you know what type of radioactivity a given nuclide gives off? Other questions are, why are nuclides radioactive? Why are there different types of decay? So a nucleus is a collection of nucleons. So that's just a collective term for protons and neutrons. So we don't have to say protons and neutrons all the time. Just call them nucleons. They're members of the nucleus. And they're held together by something called the strong force. Okay? I'm not kidding. That's the name of it, the strong force. That's a physics thing. If you want to know more about that, go study physics. It's a fundamental force of physics. It acts at very short distances, and that's what's holding the nucleons together. So the stability of the nucleus is a balance between the positive protons repelling each other, so that's a repulsive force based on charge, a coulombic force, and the attractive strong force that's pulling all of those together. You may have wondered before, how do all those protons exist in the nucleus so close together when they have positive charges, right? How does that even work? Well, it's this strong force. So you have the strong force is this attraction between all the nucleons, and then you have forces of repulsion. So you've got attraction and repulsion going on. The neutrons are an important thing in stabilizing the nucleus because they only experience forces of attraction because they're neutral. So they're not impacted by repulsive forces due to charges. So you might think, well, then lots more neutrons would be more stable. Except that nucleons also have energy levels. And so if you keep adding neutrons to the nucleus, they are going to be in higher energy levels. And at some point, the higher energy level occupied by those additional neutrons outweighs the benefit of the additional attraction from the strong force. So it's a balancing act. So we can look at the ratio of neutrons to protons as a guide for determining the stability of a given nucleus. So here's a graph showing number of neutrons versus number of protons. Come on, arrow. There we go. Number of protons. And so we see that the number of neutrons generally goes up as the number of protons goes up, but we see that it's not a one-to-one ratio. This red line would be a one-to-one ratio, equal numbers of protons and neutrons. And that's true for the smaller elements, but as you get to the larger elements, the number of neutrons is larger than the number of protons. So the little yellow dots here are nuclides that exist, nuclei that exist. The green ones, the green dots are stable. The yellow ones are not stable. Okay? They exist, but they're not stable. And above atomic number 83, there are no stable nuclei. They are all unstable. And so when you look on the periodic table, there's number 83. After 83, we see that most of these have their molar masses or their atomic masses in parentheses because they are so radioactive that you can't really give a more accurate mass for them because they're constantly changing into other things, right? So it's an approximate mass. So we see here for carbon-12, down here is a little guy. That's the stable isotope of carbon. That has a 1-to-1 ratio. Zirconium-90 is stable. That has a ratio of 1.25. We get up here to mercury, and now the stable isotope has a ratio of 1.5. So more neutrons than protons. This green line in here is sometimes called the valley of stability. So in this yellow area here, this green valley is where the stable nuclides are. Now, the type of radioactivity depends partly on the value of the ratio here. So you'll notice some of these have N to Z ratios that are higher than the stable ones, and some are lower. And so the type of radiation emitted is usually the kind that's going to bring that ratio closer to the stable ratio. So if N to Z is too high, those are the nuclides above the value of stability. They've got too many neutrons. So you're going to see radiation emitted that converts neutrons to protons, and that would be beta decay, because that's going to bring that N to Z ratio down. If N to Z is too low, it's under the value of stability, then you're going to see alpha decay. Well, you can see alpha decay. Positron emission or electron capture are going to be the main ones, where protons get converted to neutrons. Alpha decay also helps because you're losing protons and neutrons, but it doesn't help as much. Any questions? That makes sense? So, to predict the type of radioactivity, you can look at the graph. You look at the graph, look at the value of stability, and you're looking at, well, is it too low or too high on the graph? What needs to happen to bring it to the green value of stability? What if you don't have that chart available? Well, you can compare the mass number of the nuclide that you're looking at to the atomic mass listed on the periodic table. The atomic mass is the average mass of all the isotopes, right? The stable isotopes are going to contribute the most to the listed atomic mass. So for example, if you look at ruthenium-112, so it has a mass number of 112. You look on the periodic table, the atomic mass of ruthenium is 101.07. So that tells us ruthenium-112 must have like 11 too many neutrons. And so then we predict that it's going to undergo beta decay. So let's just remind ourselves what beta decay is. Oops. So beta decay is when we emit an electron, right? So ruthenium-112, the atomic number 44? Thank you. Let's try that again because I'm writing on top of other things. So ruthenium-112, atomic number is 44. So if this undergoes beta decay, we're going to lose an electron. That electron comes from the nucleus. It's not one of the electrons, and that comes from the conversion of a nucleon. So we look at this, and so now we're going to have atomic number of 45 and still a mass number of 112. And so that now is rhodium. So this one has, come on, pointer. I don't know what it's doing. Okay. The ruthenium-112, 112 minus 44. Oops. 112 minus 44 is 68. So this is 68 neutrons to 44 protons. So 1.545. And in this daughter nuclide, now we have still 68. No, wait. We have 112 minus 45. We've got 67. We've converted a neutron into an electron and a proton. So we've got 67 neutrons, and now we have 45 protons. And so that ratio goes to 1.489. So beta decay brings that ratio closer to one that's stable. That makes sense?
I don't get how you got beta decay out of any other decays, like out of alpha or...
Okay, that's a good question. Why choose beta decay? So you understand that when we're looking at this, comparing this mass number of 112 to 107, the difference in those is the number of neutrons, right? They have the same number of protons. So obviously the stable isotope of ruthenium has fewer neutrons than this one does. You okay with that?
Yeah.
So then we're going to look for a type of radioactive decay that is going to reduce the number of neutrons or reduce the ratio of neutrons to protons. So reducing neutrons or increasing protons. Okay, so if we have alpha decay, we're going to lose a helium nucleus, right? So we're going to lose 2 protons and 2 neutrons. And so that's not going to help the ratio very much, right? If we have positron emission, and I completely get that it's hard to remember, well, what's turning into the positron? What's turning into the electron? Was it the proton or the neutron? I don't have that just flashcard ready in my mind either. So this is how I would do that. I would look at it and actually write out the equation to see what happens. So then this must be 43, and this is still 112. And now it's not ruthenium anymore, it's technetium. So the number of protons has gone down, and for the mass to stay the same with the number of protons gone down, that means the number of neutrons went up, right? Well, that's the case here.
Yeah, but not the case.
That's not what we want to happen. That's the opposite direction. So positron emission is great if your N to Z ratio is too low. That'll bring it up, but beta decay is what will bring it down.
I'm sorry, what was the stability region like?
So the stability region varies depending on the size. For the small ones, it starts out at 1, and then it increases up to 1.5. So just looking at the actual number is not necessarily going to help you out at all. So if you have the graph available, you can look and see what am I aiming for. But if not, you look at the mass number of the isotope compared to the atomic mass of the element.
So if it was closer, if those numbers were closer, then that would mean...
Yeah, if this was ruthenium 102, then we'd say, well, that one's pretty stable. Or if it was 101, yeah, that's probably a stable one. And notice that when this decays, it's not ruthenium anymore. But the ratio goes in the correct direction. Yeah?
And with the electron emission, the electron is going to be on the left side of the equation, right? So that would also give us the wrong direction?
Electron capture would be the electron on the left side as a reactant. Mm-hmm.
So that wouldn't put us in the right direction?
No, that would put us in the opposite direction.
I didn't quite catch why positron doesn't work. Can you please repeat that?
Okay, so you're okay with this is a positron, and this is the equation for positron emission, right? Okay, so here we have this same starting one, so its ratio was 1.54, which we can tell by comparing these two is too high, and we want it to be lower. So then we made this happen. Let's look at the ratio for that one. So to calculate the number of neutrons, you subtract 112 minus 43, so 69 neutrons. This is the number of protons. So then the ratio is 69 over 43, which is 1.604. Okay, So positron emission made the ratio go up. Comparing this mass number to the average atomic mass tells us we need to make it go down. This is making it go in the opposite direction, so it's probably not going to happen. Okay? Anybody else have any questions? The way I would approach a problem like this on an exam is sort of a trial and error way, because usually there's enough time for that, and I've got other things going on. I don't necessarily want to memorize all of these things to an extent that I can just answer them in a flash, right? Just being able to get the answer in a minute or so is good enough, right? Okay, let's practice this. Predict whether each nuclide is more likely to decay via beta decay or positron emission. So, answering a question like this, before you look at the question there, the leads and the xenons, remind yourself what beta decay and positron emission are. So, beta decay is when we're losing an electron. Positron emission is when we're losing a positron, kind of an anti-electron. I'm just going to call it X. It's not going to be the same, but whatever. So the number of neutrons is going to stay the same. I'm sorry, the mass number is going to stay the same. Mass number stays the same. Oh, we should call it what it is. That's Z, right? I'm sorry. It's A. A is the mass number. I think it should be the atomic number, but it isn't. It's the mass number. Mass number is staying the same here. It's confusing, right? I'm just being real here. So here is Z, the atomic number for our starting thing. What is going to happen over here? Is it going to be larger or smaller? It's going to be larger, because this number plus -1 has to equal the original Z. So then this is going to be Z plus 1. And that's what happens with beta decay. Over here, if I'm starting with Z, then my product is going to have a Z that's 1 less, right? So you can figure this out as long as you know the symbols for beta decay and the positron emission. So now let's look at this. And what we're going to do is we're going to look at lead 192, and we're going to find lead in the periodic table, and we see that its atomic mass is 207.2. So 207.2. This is going to decay in such a way that it's going to get closer to this. So it needs to increase the number of neutrons, right? For lead, 82. So the number of neutrons here is 90, right? 90 neutrons. We want to increase the number of neutrons because we want it to weigh more. It's not heavy enough. And so beta decay, is it 110? Sorry. Yes, that's right. This is what happens when I try to do math in my head. Okay. Still, it needs to be higher. This is going to, now think about this, right? This is going to increase the number of protons. The mass number stays the same. So that means the neutrons go down. Here, the number of protons go down, the mass number stays the same, so the number of neutrons goes up. I know, that's not confusing at all, is it? So we're going to say positron emission. Well, let's prove it to ourselves. So 192, positron emission, still 192, but now 81. It's not lead anymore. What is it? It's, I think it's thallium? Don't quote me on that. TL. This was 110 neutrons. This was 111, right? Did we increase the number of neutrons? Yeah. You can look at, you could also think, well, if I had lead 207, what would its ratio of protons and neutrons be? Lead 207. I'm not just making that up. I'm just picking the closest whole number to the average atomic mass. That's 125, right? Check me on that. Okay. So this would be neutrons to protons, 125 over 82. 1.52. And this one would be 111 over 81. 1.37. But what was this first one? 110 over 82 is 1.34. This is the ratio of this starting isotope. This is the ratio of an isotope that's most likely stable, just based on the atomic mass on the periodic table. So when it undergoes positron emission, we get it to change from 1.34 to 1.37. Not a big change, but it's in the right direction. Does that make sense? So we just did all of this scribbly work here, and so we can just kind of write ourselves a note here. Positron to increase the Z to N ratio. Well, so this one, PB212, it needs to go the other way, right? So do we have to do all this scribbly work anymore? No, because we figured it out. So this one's going to be beta decay, because that does the other thing. And then xenon 114, atomic mass of xenon is 131.3. So this one's too low, right? Or let's do a fast comparison here. So xenon 50 is 54. So 114 and 54, it should be 60. So for this one, we've got 60 over 54. For a stable one, it would be 131 minus 54. I don't dare that one in my head. 77. be 77 over 54. So this is higher, right? Higher ratio, lower ratio. So we want to increase the ratio. So this is also going to be positron emission. Thank you. Positron. Any questions? Yes?
So then the relationship between comparing the Z to N ratio and then the molar mass is that you want where you're talking about like heading in the right direction.
Mm-hmm.
You mean like in the direction of molar mass or?
You want the molar mass, the direction of the molar mass
Yeah.
gives you information about where the ratio is going.
Okay. So you use the molar mass in terms of adjusting the ratio.
So wherever you're at, you want to go to molar mass.
Right.
So that's stable off of the.
Yeah. Or, what might be more straightforward is to do this, what I did here for xenon. So look at the ratio for the isotope that you're given, and then look at the ratio for the isotope whose mass number is closest to the atomic mass. And that's going to tell you what direction you need it to change. It's not like calculus or anything, right? But it's all twisty, right? It's kind of like figuring out how many electrons get lost or gained when you've got a -3 ion, right? Because you're adding negatives, and so that gets confusing. Any other questions? So it turns out that the actual number, not just the ratio of protons and neutrons, can also affect the stability. And there's, people spend a fair amount of time just looking for patterns and connections and things. So a large number of stable nuclides have both an even number of protons and an even number of neutrons. This seems kind of weird, right? Just that's been observed. So here we go. Even Z, even N, number of nuclides like that is 157. And ones with an odd-even combination, 53 of one, 50 of the other, only 5 stable nuclides have both an odd number of neutrons and an odd number of protons. And there's actually a reason for that. Nucleons have a tendency to pair up, much as electrons do. And we don't want to go into why they do that or how or anything. That's just, they do. And we'll leave it there. So these are called magic numbers. The nucleons are occupying levels, and they're going to pair up. So we see that atoms with certain numbers of electrons are uniquely stable, right? The noble gases. We also see that atoms with a magic number of protons or neutrons are uniquely stable. So the magic numbers are 2, 8, 20, 28, 50, and 82. Also, n equals 126. Notice that all of these magic numbers are even. So you could have neutrons or protons being any of these, or the number of neutrons being 126. I do not expect you to memorize those numbers.
So what would be the use of those numbers? Like, what would be?
Well, what would be the use of those numbers? That's an excellent question.
You know, having periodic
To make them easier?
If you were trying to pick between 28 and 29, you'd go with 28, right? But really, it's more of a, oh, look at this. Isn't this kind of crazy? Just sort of a fun fact about.
So it's not really anything we're going to apply.
I don't think you really need to do anything with this. No. But it's there. There it is. I told you about it. I'm not going to test you on magic numbers. It would be interesting to see if those are magic in terms of like the California lottery or something. Okay, so radioactive decay series. If you look at those products that we were predicting in the previous example, those products weren't stable either. They were just going in the correct direction, right? So what happens is you have one nuclide decaying into a daughter nuclide, but that daughter is often unstable as well, and so she'll decay, and it's sort of like this generational family tree kind of a thing going on here. So atoms over 83 are radioactive. They're going to decay in one or more steps. Generally, it's alpha and beta decay. Those are the big two. Gamma decay comes along with those. It doesn't involve particles, but that's where all the excess energy goes. And the radioactive decay is just going to continue until you get to a stable nuclide. So this is the decay path or series for uranium-238. It goes to thorium-234. And here, alpha decay is going to decrease the number of protons, so it's going to move to the left. And beta decay is going to increase the number of protons, and so it's going to move to the right. And so then we've got, come on, pointer, seriously. See if that helps. Okay, I can't point. Anyway, it goes down, and you notice that the isotopes are getting smaller, right? It can't decay into it doesn't decay into a much larger atom. It goes smaller. And that's not because you can't increase the number of protons, but that's because things over an atomic number of 83 are all unstable. And so if it goes up there, it's still going to come down. And so we end up here with the final, oh, the pointer's back, except it's also up at the top. We end up down here at 82 with lead-206. And I do not expect you to memorize that. Don't even try.
So these decays, if you try uranium, it's guaranteed to go through the series.
Yeah, this is the series that uranium-238 goes through. And they, people have studied all of the different isotopes, and you could look them up. Oh, if I have this, what's going to happen to it? Well, it's going to do this, this, and this.